Welcome to Chemist Twist on Culinary Specialists with Professor Herold and Professor Cranford and Loyola. Today's lesson is to show how chemistry is in everyday life, and today we'll be cooking spaghetti. The materials you'll need for today is ground beef, some ragu, pasta sauce. We're going to have 2 pots, and some salt, and measuring cups. And all this can be looked up in your active chemistry book. The activities we'll be using for today is on chapter 7, activity 1, 2, 3, 4, 6, 7, and 8. Now, to begin with, can anyone tell me what kind of heat transfer energy we're going to use today? Well, I'll tell you. Today we're going to use convection, and on activity 1, convection is a transfer of heat energy by the physical motion of masses of fluid, either liquid or gas.
So I have a question. How much energy is required to boil water?
Very good question. On activity 4, this talks about heat vaporization. 540 calories is used to heat 1 gram of water to turn into 1 gram of vapor water. And that is a very good question, but that's not what we want in this experiment. We just want to boil water so we can boil the spaghetti. Later on in this episode, you'll see Professor Herold boiling spaghetti.
Supposedly, if you add a pinch of salt to your boiling water, you will reach your boiling point faster. Does anyone know what the salt would be known as if this statement is true? Yes, you over there.
A catalyst!
Correct! How did you know? In activity 2 in your chemistry book, it explains a catalyst as something that lowers the amount of energy needed to start and maintain a reaction by providing an alternate pathway.
Could you say that in English, please?
Yes. A catalyst speeds up the reaction by needing energy to break bonds of the water, giving off more heat to its surrounding, and this is known as an exothermic reaction. Then the heat makes the temperature rise, giving you a faster time for the water to reach its boiling point. On this special episode of Chemist Twist on Culinary Specialists, we will test if salt can really be at fault for your burnt food. In order to do this, we will have 2 pots with 2,000 milliliters of water in each of them. The exciting part is we will have a pinch of salt in one of the pots. We will record each pot's water temperature till it's at a boiling point of 100 degrees Celsius, or at this elevation, around 95 degrees Celsius. Professor Cranford, what is the starting temperature?
Right now the temperature is at 25 degrees Celsius.
Alright. In order to figure out how many calories we will need to boil water, we will use the formula Y equals mc delta T. M is the mass, or the milliliters of water. C is the constant, and for water, it is 1 calorie over 1 gram degrees Celsius. Delta T is the change in temperature. Let's do this!
As the water is boiling, we're going to work on denaturing the proteins. Activity 7 describes denaturation as the process in which a change in protein shape occurs as it unravels and expands outward, still keeping its primary structure.
Professor, how does this relate?
As the meat starts to cook, it'll expand outward, but it'll still keep its primary structure.
Oh. Fellow professors, what is the temperature for each pot of water?
Mine's at 95 degrees Celsius.
Mine's at 95 too.
As you can see, they are both at 95 degrees Celsius, so it does not matter if you add a pinch of salt or not. By previous research, I found out that you would need 230 grams of salt for 1 liter of water just to raise it by 2 degrees Celsius. That's a lot of salt. To To figure out how many calories was needed to boil our water for our tasty spaghetti, Professor Cranford, the math lead when she was in high school, will explain how you figured this out.
So the energy required to determine how many calories needed to boil the water, we use the equation mc delta T. M is the mass, which is 2,000 grams. C is the constant, which is 1 calorie per 1 gram degree Celsius. And delta T is the change in temperature. Our starting temperature was 25 degrees Celsius, and it went up to 95 degrees Celsius, so the change in temperature was 70 degrees Celsius. The next line shows how the grams and the degrees Celsius cancel, leaving us with calories. So we take 2,000 times 70 equals 140,000 calories. As you can see, while the meat cooks, it expanded outward and is starting to change color, but it only performed a physical change, not a chemical change. Now that the meat is cooked, we will add the sauce. Today we are using the famous ragu in a can.
Question, is it true that all canned foods keeps bacteria out?
Yes, it is true. In Activity 8, it explains how when you put a can into water over 100 degrees Celsius, it extracts all the bacteria from within the can and outside of the substance that's in the can. When you take the can out of the water and it's cooled, the pressure on the outside of the can tightly seals the lid, and it keeps it from any bacteria entering inside of the can or getting into the substance that's in it. So we're going to add the sauce, and the final step will be to let the sauce and the meat cook together. While this is cooking, we'll do a recap on everything that has happened so far. Alright, at the beginning of the experiment, we used convection from the flame to cook. We then found the boiling point for vaporization of the water. We did an experiment on boiling H2O with salt and without to see if the salt worked as a catalyst to speed up the reaction, but we found out that it didn't work as fast as it should. We also talked about breaking bonds in an exothermic reaction, about how it gave off energy rather than an endothermic reaction where it absorbed energy. Talk about the calories it took to do both. And finally, we denatured the proteins and added the sauce, and we talked about canning with that. Here's our final product, this plate of spaghetti.
It looks good!
It smells good.
I'm sure it tastes good too. So if there are any further questions, please read our essay following the report. Thanks for watching, everyone. So our final project was the spaghetti.